So for this part of the video, I'm just going to go back to looking at that binary search tree, and that's the one that we had looking a bit like this. It's got nodes in it, and it's making that tree structure, and then down here we've got some nulls to indicate where the end of our tree is, and if both items are null, then we've probably got a leaf node. So the binary search tree algorithm, this one is really similar to the one presented in the lecture slides. The only difference is I'm returning a boolean rather than an item. So basically the first thing we do is our base case, which is if the item isn't in the tree. So if we reach null on our node, then we're going to return false. Otherwise, if we do find the item, we're going to return true. Then it's just a simple recursive call to the left or right, depending on which way we need to work down that tree. So the implementation of this function is really quite simple. I've given it a more Boolean style name, but it's just got some public access, which is going to take in that data or the item which we are searching for. Of course, if there's nothing inside the tree, we're going to return false. Otherwise, we're going to make a call down to our private implementation, and that's just going to start at the root and take that data in with it. Of course, if we've reached the end of searching, we're going to return false. Our other base case here is if we've found the item, and we're going to return true. Otherwise, we're just going to make calls to the left or the right as needed. So the next thing I want to look at is deleting a node from a binary search tree, and there's a couple of things we need to remember when we're deleting a node, and that is that we want to preserve the properties of the tree, that being that all left children are still going to be lesser than its parent, and all right children are going to be greater than its parent. So when we're deleting, there's a couple of cases which we need to consider. We need to consider the case of a leaf node, which is actually incredibly easy. We then need to consider the case of a node with only one child, how we would delete in that case, and then how we go about deleting a node with two children. Two children is a little trickier. That's where we're going to have to work a little harder to preserve the integrity of the tree. Looking at the case of a leaf node, that would be pretty simple. So all of these guys are our leaf nodes. These guys are really easy to remove. Let's say we wanted to remove 25. All we'd have to do is just take him out. There's nothing we have to change internally in the tree. Everything still works, everything's still fine, and the integrity has been preserved. But let's say we wanted to delete a node with only one child. This is another fairly simple case. So if we look over here at 5, we can see that 5 only has one child. Now that child can have any kind of tree structure underneath it. It doesn't really matter what tree structure it's got, or if it's a single node. The important thing to notice is that 5 is the node that only has one child. So this one is, again, really simple. All we need to do set the parent's pointer down to this node down here, the child node, and then we just get rid of 5, and then the integrity of the tree is preserved, the whole structure is still there, everything will still fall into place. So finally, let's say I want to delete a node that has two children. This is slightly more complicated, but you'll see it'll reduce down to being really simple again. So what happens is, let's say I want to delete node 17, and this has two children, and they both have some kind of arbitrary tree structure below them. I can't just get rid of the node because that would leave the tree fairly broken. I can't just reapply this link here because I've got two children to take care of, and if I set this link, then I'm losing the whole right subtree. You know, if I do it that way, then I'm losing the whole left subtree here. So what I need to do is I need to find some way of fixing the tree, and it'll help if we've got some values here. But what I need to do is find a way of preserving the integrity of the tree while getting rid of this guy 17. So there's actually two approaches I can take. I can work with approach 1, which would be to replace 17 with the minimum value from the right subtree. So that means I can go down here and I can see that, okay, 18 is the smallest guy in this entire tree, and that means he's going to be replace 17 here. I know it'll work because he's coming from the right tree, which means he's larger than everything down here. But by selecting the smallest guy, he's going to be smaller than everything down this tree. So it will still keep my tree's structure correct. The other approach I can take is approach 2, which is just where I take the maximum value from the left subtree, and that would be this guy here, 16. I would bring 16 up to here, and then the tree again would still be preserved. It doesn't matter which way I go. For my example, I'm just going to go with approach 1, which is where I take a copy of 18 and I place it over here, and I put 18 here instead of 17. Now I've got the unfortunate issue that I've got 18 still left over down here. So this is actually the guy I want to delete, and as you can see, this is actually a leaf node, so he's pretty easy. I just get rid of him. To show you how that could look again, let's say this time I want to delete 18. Okay, so I'm just going to grab 19 because that is the smallest. The only difference is, in this case, 19 has one child. So I take a copy, I bring it up, and I move it like that. But now when I come to delete him, all we have to do is reset the links, and then we've got our tree structure preserved. Okay, so those are the approaches. Essentially what you want to do is you just want to look for the minimum in the right subtree and reduce down to case 1 or case 2, depending on whether it's a leaf node or a node with only one child. Alternatively, you can look for the maximum value in the left subtree and then reduce it down to case 1 or case 2, and that will work. So in order to remove these nodes, what I've done is I've made some changes to node. Basically, I've got some Boolean identifiers now, which are just going to let me know if the node is a leaf, does it have one child. If it doesn't meet either of these two conditions, I can easily assume that it's going to have two children. And in a similar strain, I can identify if the node happens to be a right child. If it's not a right child, I can easily conclude that it's a left child. I'm also keeping track of the parents now. It's just easier, I think, to do all of our link and maintenance when we're removing if we know who the parent node is at any given point. That means I've had to make a change in my add function here, and basically when I'm creating nodes, which is here I'm setting a right child of the current node, I'm just passing in the current node as well, and that's going to be taken as a reference to the parent. I'm doing it here when I'm doing left children as well, and you can see here in node the second item now is the reference to the parent, and that's just going in and getting set up there. So for the remove function, it's fairly simple to begin with. First, we just want public access, and this one's going to take in that item that we want to remove. My function is going to return a boolean just to let me know whether the item was removed or not. But anyway, so if there's no nodes, I'm just going to return false because I know I haven't been able to remove the item. Otherwise, I'm just going to make a call down to that private function, and I'm going to pass in a reference to the root and then also the data which I want to remove. Once I'm down here in the private function, essentially if I meet the case where the current node is null, then I know that I haven't been able to find the item to remove it, so I'm just going to return false. If the current node isn't the one I'm trying to remove, I can make calls to the right or the left as required. It gets a bit tricky though in the case where I've found the node to remove. So we'll go through each of these. Basically there's just case 1, case 2 and case 3, which is what we were talking about before. So in case 1, basically if the current node is a leaf, then I know that I'm working with case 1, and it's going to be slightly different depending on whether I'm working with the root or whether I'm working with any other kind of leaf node. If I'm working with the root, I just need to make sure that I set the root to null. I've just got to be very careful with all of my maintenance of pointers and things. In the case of a normal node, what I want to do is I want to say, okay, am I a right child or a left child? If I'm a right child, basically I'm going to get that parent reference and I'm going to make sure that the parent's right is set to null. If I'm a left child, I'll get that parent reference and then I'll make sure that the left child of that parent is going to be set to null. And then at this point, I'm going to delete the node and then I'll just decrement the number of nodes in the list. So case 2 is a little bit different. I've been able to identify case 2 by saying, okay, the current node has only one child. What I do is going to depend on whether it's the root node, and in this case, this means that the current node is the root node. In this case, it's going to be a bit different. Basically, depending on whether it's got a left or a right child, whichever child it's got is going to have to punch up into the new root position. So that's not too hard. All I need to do is identify, okay, is it the right child? If it is the right child, great. I'm going to grab that right child and then I'm going to set its parent to null. At the moment, its parent is the current node, but we're going to set it to null because the root node doesn't really have a parent node. Then all I need to do is just set the root of the tree to that right child. Same thing on the left. So if it's a left child, I'm going to get that left child and I'm going to set its parent to null. Then I'm just going to set the root of the tree to that left child. If I'm removing any other node, it's going to depend on whether it's got a right child or a left child as to which way it goes. So basically, if the child it's got is a right child, what I'm going to do is the first thing I'm going to do is I'm going to get that right child and I'm going to set the parent link to it and I'm going to set it to the current node's parent. So I'm just going to make sure that that link there is set. Then what I'm going to do, if the current node happens to be the right child of its parent, then I know that I'm going to get the parent and I'm going to set its right child to the current node's right child. If it's the left, so if the current node is the left of its parent, then I'm going to get the parent and I'm going to set its left child and I'm going to set that to the right child of the current node. So in this one, it's basically the same as up here. It's just that we're going to get the current node, we're going to get its left child, and we're going to reset the parent of the left child, and we're going to set it to the parent of the current node. And then depending on whether the current node is a right child, so if it is the right child of the parent, then we're going to set the right of the parent's right is going to get set to this left child of the current node. Otherwise, the parent's left is going to get set to the left child of the current node. That's literally the hardest part of this entire algorithm. So hopefully you can follow that. Then we just need to do some little bit of housekeeping. We just delete the current node and then we decrement the number of nodes in the list. So for this third case, if the node has 2 children, this is actually one of the easiest to implement because we are going to use the recursive call. So all of the hard work is going to get done in either case 2 or case 1. So basically all I have to do is I'm working on the right side, so I have to find the minimum node from that right side. So I've just got a little helper function here. It's just going to take in the reference to the right child and then it'll keep looking down the left branch of that right child until there are no more left children. And at that point we're going to know that we've got the smallest node and we can return that. And then I'm just going to keep a reference to that. Once I've got reference to that, I'll quickly take a copy of its data because that's going to come in handy. We're going to use that. What we're going to do is take that copied data and set it as the data for that current node. Before I've done that though, I'll call remove on this temp node's data. This would definitely be quicker. Let's just go temp node. So I just want to remove that node, and it's going to get caught up in case 1 or case 2 depending on how many children it has and how it's going to be removed. So yeah, that's pretty simple. Finally, all I have to do is return true at the end of this condition here to show that I have removed an item, and I'm returning false otherwise. So we just want to do some testing on that to make sure everything runs fine. So this is just an extension on last week's video. We're adding some accounts to the tree. It's the same as last week, but I've just got a new account here. It gives me better test coverage when I'm trying to remove the nodes. Basically what I'm going to do is I'll just test that has function if I can find it, and if I can find an item in the tree, I'm going to print out this line. If I can't, I'll print out that line. And then finally, I'm just removing nodes. I've done it in a slightly strategic order just to test all the different cases to see how I've gone. I might be missing 1 or 2 cases, but I think I've got fairly good coverage on that. So this is how it runs. You can see we're just setting up that tree. I've done a search for account 12 and that's showing up. Here I removed node 6 and you can see it's been removed. I try and remove it again just to see how it goes when trying to remove an item that doesn't exist in the list, and that's working fine. Removing node 21. You can see that's been removed. Now I'm removing node 8, and you can see 9 has punched up into 8's place, so that has definitely worked correctly. Then I removed node 12. That's the case with 2 children, and it happens to be a root, so that's quite interesting. And 15 has punched up into 12's place, so that is definitely working. Then I removed node 15, and that's the root case again. 9 has punched up. And then I just removed node 9. I try to print, and of course there's nothing to print at this stage. So that's the end of the videos on binary search tree. A couple of techniques and functions in there. You'll probably still need to add some of your own stuff like a destructor, but yeah, good luck with implementing your own.